Welcome back. So in this section, we're going to be talking a little bit more about what's going on under the hood. So it's a little more theory, a little less project based, and it's really just about trying to understand what are these weights doing. What can I kind of attach my mind to when I'm thinking about a neural net training that's going to help me be able to debug it, help me be able to find better signal and cut out better noise. Just have a framework to work from to think about things like that. So the things that we know, right? So we're taking this one that represents excellent, right? And we're summing it into layer one and we're making a prediction. Now, there's an interesting phenomenon that happens when, especially when you have linear layers right here. And I talked about this before very briefly when I was saying that we wanted to have a linear layer here. And I said that I would talk about a layer, and now's the time. When we have a linear layer like this, that's making a prediction, what's really happening is these four, well, in this case, or more, however many you set it to be, weights are feature detectors. What they're doing is they're trying to detect a certain state in this neuron, or this neuron, or this neuron, or this neuron, right? And so if this is like a big negative number, this is looking for this to be a big negative number. But if this is zero, or if this is a positive number, it's going to have the opposite effect, right? So these are looking for a certain set of states. It's looking for a 0.5, 0.9, and -2, right? So, there are certain hidden layers that cause this to output a high number, and there are certain hidden layers that cause this to output a low number. And it's just a weighted sum. Like, it's actually pretty simple, right? If these are positive in all the same times, or all the same ways that these weights are positive, then this puts a lot. But if this is positive and this is negative, and this is positive and this is negative, and this is positive and this is negative, and this is positive and this is negative, then this ends up being a really, really low number, right? So when these have the same polarity and have high values in all the same places, this makes a high prediction. So what does that mean for all this stuff back here? Well, horrible and terrible, when we think about what commonly happens in our data set, they're associated with negativity, right? Excellent and fantastic, if that was another word up here, are constantly trying to predict this one. They're trying to be, relate to this vector in a certain way, right? So what's interesting is that if these words are being trained, they're just rows in a vector, rows in a matrix, right? They're being trained to manipulate this in the same way, right? To create a high value or a low value. What does it mean that when we learn here, when we backpropagate gradients and we update these to both exhibit the same phenomenon over here? Like, horrible and terrible are both supposed to affect this node in the same way. And as we're updating these weights to cause them to do that, what happens? Their weights become similar. Why? Because both of them have the same goal, right? So if this one predicts positively, this thing's gonna go, no, 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 no. Update your weights, Mr. Horrible Vector, and be a little more like this, because this is what causes me to predict negative. That's what backpropagation is all about. It's all about this node being able to tell these weights how to be better, how to be more accurate, right? And because it's sending the same signal to horrible and terrible, right? Be negative, right? They end up congregating together, and it's really quite cool. So check this out. So I've got kind of a heuristic for seeing how similar the different vectors are for each word. And now we can go through and we can say, okay, show me the vectors, the words that have the most similar vector to excellent. I'm just using a simple dot product. Excellent, perfect, amazing, today, wonderful, fun, great, best. And this is on a trained neural net. Look at that. After we trained, because these words, excellent, perfect, amazing, all were supposed to create the same effect, or a very similar effect on the output, they were given similar weights. Inversely, if we say the opposite, we say terrible, worst, awful, waste, poor, terrible, dull, poorly, disappointment, fails, disappointing, boring, unfortunately. It just goes on and on and on. This is actually an even better filter than our original counts. Our counts had these weird names in them, and there's this other noise, but this is awesome. It's clear. It's evident that the network has figured out that these words are related, right? These words are both trying to create the same effect on the output data, right? Now, to be clear, we can't overstate this. It doesn't know that these have the same meaning generally. All it knows is that they have the same meaning in the context of this one output neuron, because it's the only output neuron there. They exist to create the same effect to this neuron. Now we had a bunch of different neurons that were you know, pushing it in one way or another to be the same or different in a bunch of different ways. This could get a lot more complicated. But basically, it grouped words by sentiment, right? It said, hey, all your negative words have a really similar vector coming out of you, and all your positive words have a really similar vector coming out of you. And that's a really powerful intuition, because that means you can look at a neural net like this and you can say, okay, we're going to train it for this. So it's probably going to group these vectors like this and these vectors like this. And you can kind of start to think about, what's going on under the hood and how you can, once again, identify signal and noise. Because that's what framing the problem is really all about. Now, to kind of add a bit of extra kind of jazz to this, what I'd like to do is something that's called TF-IDF. So TF-IDF, what it does is it takes a high dimensional vector, and in our case, high dimensions might just be 4, right? And it clusters them into 2 dimensions, or some other, however many you pick, so that we can plot them on an XY graph and see how they're naturally clustered in the higher dimension. And the cool thing is that we can do that here. So, and what I'm going to do is I'm going to cluster them, but then I'm also going to say, hey, the words that our ratio said were really positive, I'm going to make them green, and the ones that were really negative, I'm going to make them black. And so, in theory, because all these vectors are really similar, it should cluster, or it should show how they're clustered already. And look at that. So there's a couple that are scattered in between, but the neural net has clearly separated them. So like there's this big, long negative cluster, and then these really nice positive clusters. Let's take a look. So I think we can add labels here. I left them in. That was kind of messy. Check this out. So you click that wheel zoom, you can kind of look in. Oh wow, interesting. So unconvincing, dimensional, lousy. Look at this. Extraordinary, lovable, provoking, award, touched. It's beautiful. It's awesome. So we can kind of look around. So this, maybe we'll call this a vector space, right? So, and actually, you see the ones that are kind of agnostic are like some of those names, right? So this is kind of a little bit of a noisier one. It's like Dan is right there. But still, it did a really good job of clustering vectors by sentiment automatically, right? So I guess I told it to do this because I gave it train data to allow it to do this, but all it was trying to do was predict accurately. But implicitly, while it was trying to predict accurately, it had to group these words to have similar different vectors so that it could classify them, in aggregate when they were all summed together as being more positive or more negative. And that's what the neural network did. And it's really cool to see it kind of behave this way. And so so I guess to close, like this is what neural nets are all about. This is what framing the problem is all about. It's about understanding what's going on under the hood so that you can reduce the noise as much as possible, increase the signal as much as possible so that it can find the structure that you're interested in it finding. We didn't tell it that lovable and extraordinary were similar terms in this context, right? All we said was, hey, all these reviews are positive, all these reviews are negative, figure it out. And it figured out which terms were similar, which terms were different, and I was able to do that to make accurate predictions. So I hope you've enjoyed this segment, and yeah, we'll see you soon and continue to enjoy your course.